Have you ever wondered what lies at the heart of the universe, hidden in the cloak of darkness and mystery? This question has driven humans on a quest for understanding, leading us to the enigmatic concept of black holes. These celestial bodies, shrouded in secrecy, have fascinated and perplexed us for centuries. Let's journey back in time to the 18th century when two brilliant minds, John Michel and Pierre-Simon Laplace, first predicted the theoretical existence of black holes. They speculated about dark stars, whose gravity was so strong that light could not escape. Their predictions, while initially met with skepticism, laid the groundwork for our current understanding of these cosmic anomalies. However, it wasn't until the 20th century that these theories began to gain traction. Enter Albert Einstein, a name synonymous with groundbreaking scientific thought. With his theory of general relativity, Einstein revolutionized our understanding of gravity, space, and time. His equations suggested the existence of regions in space where matter could be compressed to a point of infinite density, a singularity. That's right. The concept of black holes is rooted in Einstein's revolutionary theory. But even Einstein had his doubts. Despite his own equations pointing towards their existence, he struggled to accept the concept of a celestial body so dense, so powerful that nothing, not even light, could escape its gravitational pull. He considered them merely theoretical constructs, an oddity of his equations, not something that actually existed in the universe. Yet here we stand, a century later, with black holes now an accepted part of our cosmic landscape. We've come a long way from Michel and Laplace's early theoretical predictions and Einstein's groundbreaking theory. The journey to this acceptance has been filled with scientific debate, rigorous research, and the relentless pursuit of knowledge. The black hole, a celestial body so dense that not even light can escape its gravitational pull, was born from these scientific advancements. As we delve deeper into the mysteries of the universe, who knows what other enigmas await us in the vast expanse of space? As our understanding of the universe expanded, so did our knowledge of black holes. These enigmatic objects are the ultimate result of gravity gone wild, born from the remains of massive stars that have exhausted their nuclear fuel. The formation of a black hole is a dramatic affair. A massive star, many times the size of our sun, collapses under its own weight. As the star implodes, it forms a singularity, an almost infinitely small point in space, where gravity is so strong that nothing can escape, not even light. This threshold where gravity becomes irresistible is known as the event horizon. It's the point of no return. There are different types of black holes, each unique in their own right. Stellar black holes are the most common, formed by the gravitational collapse of a single star. They can weigh up to 20 times the mass of our sun, yet they are so small that you could hold one in the palm of your hand. Supermassive black holes, on the other hand, are the behemoths of the universe. Found at the centers of galaxies, including our Milky Way, they can contain millions or even billions of times the mass of our sun. Then there are the intermediate black holes, the Goldilocks of this cosmic family, not too big and not too small. These black holes are still a subject of ongoing research, and their existence offers tantalizing clues about how their supermassive siblings form. But black holes aren't just cosmic vacuum cleaners, they might not be eternal. The physicist Stephen Hawking proposed that black holes can slowly lose energy through a phenomenon now known as Hawking radiation. According to this theory, black holes could eventually evaporate entirely, although this would take longer than the current age of the universe. Stephen Hawking's breakthrough suggested that black holes might not be eternal, introducing an element of fragility to these cosmic beasts. This concept shakes up our understanding of these celestial objects, adding a new layer of complexity to our exploration of the cosmos. Black holes aren't just space oddities, they challenge our understanding of the universe itself. As we delve deeper into the mysterious realms of black holes, we encounter the information paradox. This is a conundrum that exposes a fundamental conflict between quantum mechanics and general relativity, two of the pillars of modern physics. You see, quantum mechanics insists that information can never be lost, while general relativity, in the context of black holes, suggests that it can. This paradox has been a thorn in the side of physicists for decades, sparking intense debates and leading to radical theories about the nature of our universe. Now let's dive into the speculative existence of micro-black holes. Unlike their stellar or supermassive counterparts, these are minuscule entities, potentially as small as a single atom, yet with the mass of a mountain. The intriguing part is that these hypothetical black holes could be remnants of the Big Bang, carrying secrets of the universe's birth. And here's where it gets even more fascinating. Theories suggest that micro-black holes might be the building blocks of wormholes. Now, wormholes are essentially bridges connecting different regions of space-time. Imagine, if you will, a cosmic shortcut. This leads us to one of the most tantalizing possibilities: time travel and the existence of multiple universes. Do multiple versions of reality exist, each branching out from every decision we make? Could we potentially travel back in time or into the future through these wormholes? While these ideas might seem straight out of a science fiction novel, they are serious subjects of study in the realm of theoretical physics. Black holes, thus, became a gateway to uncharted territories of science, promising answers to questions we didn't know we had. And while we may not have all the answers yet, the exploration of black holes continues to push the boundaries of our understanding, reminding us that the universe is far more complex and wondrous than we could ever imagine. Our journey into the heart of darkness continues, with new discoveries and theories emerging. In the quest to understand black holes, we've made some significant strides in recent years. Take, for instance, the first ever image of a black hole. In 2019, the Event Horizon Telescope collaboration stunned the world by releasing an image of a supermassive black hole located in the galaxy M87, over 55 million light-years away. This was a watershed moment in astronomy, giving us a peek into the abyss of a black hole's event horizon for the first time. But the revelations don't stop there. Astronomers have also been able to detect the ripples in space-time caused by black hole mergers. These mergers, when two black holes coalesce into a larger one, send out gravitational waves that ripple across the cosmos. The detection of these waves, as confirmed by the Laser Interferometer Gravitational Wave Observatory, or LIGO, has opened up a whole new way of observing the universe. Now let's talk about dark matter, that elusive substance that makes up about 85% of the matter in the universe. Researchers are looking into the possibility that some of the dark matter may be made up of primordial black holes that were formed not by collapsing stars, but in the high-density environment of the early universe. If proven, this could significantly advance our understanding of both black holes and dark matter. And then there's quantum gravity, the holy grail of theoretical physics. Quantum gravity aims to reconcile the contradictions between quantum mechanics and general relativity as they apply to black holes. This is a field of ongoing research, with scientists around the world working tirelessly to crack this cosmic conundrum. These recent advancements take us one step closer to unlocking the secrets that black holes hold. As we stand on the brink of scientific revolution, black holes continue to intrigue and baffle us. Their elusive nature, coupled with their immense gravitational pull, makes them one of the most challenging celestial bodies to observe. They're like the universe's best-kept secret, hidden in plain sight, yet cloaked in mystery. Yet despite these observational hurdles, we've made significant strides in understanding these enigmatic entities. We've discovered that black holes vary significantly in size. Some are as small as just 20 miles in diameter. These are known as stellar black holes. On the other end of the spectrum, we have supermassive black holes, which are millions or even billions of times the mass of our Sun. The largest of these known to us, TON 618, is estimated to have a diameter of 200 billion miles. That's about 40 times the distance from the Sun to Pluto. These massive entities aren't just large in a physical sense. Their gravitational influence extends far beyond their physical boundaries, bending and warping the very fabric of space-time around them. This leads to some truly mind-boggling phenomena, like gravitational lensing, where the light from distant stars is bent around a black hole, creating a cosmic mirage. But perhaps the most intriguing aspect of black holes is something known as extreme time dilation. This is a direct consequence of Einstein's theory of relativity, which states that the stronger the gravitational field, the slower time passes. So if you were to venture close to a black hole, time would slow down for you relative to someone further away. In essence, time and space switch roles inside a black hole, causing what we perceive as time to become a spatial dimension. Did you know that inside a black hole, time and space switch roles, leading to what is known as extreme time dilation? It's just another mind-bending fact about these cosmic enigmas that continue to captivate us as we journey further into the heart of darkness.